Hi, my name is Sheng. I'm from the RobotMed lab at Georgia Tech. In this video, a fiber optic rotation sensor for Meso-Scale Torsion Actuator will be presented. A lot of surgical robots have been developed for minimally invasive surgery. To precisely reach a target, the robot shape needs to be measured in real time. There are several shape sensing techniques, such as FPG strength sensing, EM tracking, and so on. We are developing a neurosurgical robot for intracranial hemorrhage evacuation. On this robot, a shape memory alloy torsion actuator can realize tip articulation, but there is no existing solution for its motion feedback due to several limitations. Meanwhile, fiber optic sensing based on light intensity modulation has been widely used for displacement and force sensing. In this work, we have developed a fiber optic rotation sensor for this neurosurgical robot. This slide shows the prototype of the sensor and the actuator. Both have a diameter of 8 mm. Their structural components are 3D printed from plastic material. To assemble them, the sensor shaft is connected to the actuator shaft by press fitting. The other end of the sensor shaft is connected to a reflective rotor. We have fabricated two types of rotors. One has a slanted reflective surface, and the other one has a spiral reflective path. When the actuator rotates, the distance between the reflective surface to the fiber tip continuously changes. Therefore, the light intensity received by optical fibers will be modulated, leading to varying voltage output. To calibrate the rotation sensor, the sensor shaft is actuated by a DC motor. To optimize the sensor design, voltage output is compared among different designs. It's observed that a brass rotor generates higher voltage output than a luminous rotor, probably due to its high reflectivity. We tested two different commercial optical fibers, and the Cairns FU24X is a better choice. It's also observed that the voltage output by the Type 1 rotor is continuous and more smooth than the Type 2, and it also fits the model prediction better. Therefore, the Type 1 brass rotor is used for the rotation sensor. Based on the calibration results, the root mean square measurement error is about 2 degrees for a slow motion of 120 degrees. The rotation sensor is integrated to the SMA torsion actuator to evaluate the control performance. The integrated system is fixed on a fixture, and the actual rotation is measured by a rotary encoder. With the motion feedback from the rotation sensor, the actuator is controlled by a PID controller. The average steady-state error for stepwise references is about 0.2 degrees. In the end, tip articulation of the neurosurgical robot is demonstrated. The robot tip is capable of rotating 120 degrees by following stepwise references or linear references. We are planning to integrate more sets of optical fibers to improve the measurement range and precision in the future.